Hello and welcome everyone for video lecture series of Design of Steel Structures. Myself Sudhir Begaike, Assistant Professor, Department of Civil Engineering, Sanjeevani College of Engineering, Kopargaon. So in the previous video, we have started with introduction to third unit B part, that is design of bases. In introductory video, we have seen what are the different types of bases. Basically, two types of bases we have seen: slab base and gusseted base. We have seen the differentiation between two bases, when slab base is to be adapted and when gusseted base is to be adapted. What are the component parts of slab base and gusseted base, and again what are the different design steps that are to be adapted in case of slab based design and gusseted based design. So in this particular video, we are going to solve one numerical on design of slab base. So for that, statement is given: design a slab base for a column using ISHB 350 at the rate 710.2 Newton per meter. So that description is given in order to copy the properties from your steel table. So the details are ISHB 350 subjected to factored load of 1500 kilonewton. So the total compressive force acting on your column or section is 1500 kilonewton. The load transferred to the base plate is by welded connection and the base rests on concrete of grade M20. So as we have discussed in the previous video, that details regarding your related with your connection and what is the concrete base grade given, that is already mentioned as a given data part. So here characteristic strength of concrete FCK value is given as M20 value, correct? And again they are mentioning that connection between your rolled section column and base plate is with the help of welded connection. Usually such type of statement, if it is not mentioned in the problem, you may consider there is direct bearing between your base plate and column and load is partially transferred to your bases. In that cases, instead of going for designing the weld size or your number of bolts for total load, you can partially consider half of the load, right? So here, as that particular condition is not mentioned, we are assuming that entire load will be transferred from your column to base plate, and that is to be transferred with the help of welded type of connection, correct? So this is the given data I have written. In given data, ultimate strength of your plate or steel is Fu 410 MPa, yield strength 250 MPa, characteristic compressive strength of concrete FCK value 20 Newton per mm square or MPa, then partial safety factor for welding, that is purposefully I have considered 1.5 because two values are there. For field fabrication we are adapting 1.5 and for fabrication or in shop welding we are going for 1.25, but this particular section, that is slab base, is going to be erected exactly at site, and that location only we are going to provide the welding. Therefore purposefully partial safety factor I have considered as 1.5, correct? So according to the given data for ISHB 350 710.2 Newton per meter, I have copied on the properties: thickness of flange, thickness of web, total depth, that is H value or D value, overall depth, and width of flange as 250 mm, correct? So these design steps for slab base we have already seen in that video. So step number 1 we are going to start. So step number 1 always starts with calculating your bearing strength of concrete. So as per IS 456, bearing strength of concrete. So step number first, bearing strength of concrete, and it is given as 0.45 into characteristic compressive strength FCK. So that is given as 20. So 0.45 multiplied by 20 is equal to 9 Newton per mm square. So this is the amount of bearing pressure that is going to act on your solid plate or steel plate from bottom side, that is 9 Newton per mm square. For using this pressure you need to calculate the area required, correct? So step number second, area required for base plate, is equal to, so area required is calculated as area required equals to total load acting divided by your bearing strength, that is 9 Newton per mm square. So need not write this unit, it is not required. So total load acting on the section divided by your bearing strength we have calculated as 9 Newton per mm square. So area required will be equal to, so I am getting value of area as 166,667 mm square. 667 mm square. So this is the amount of area in order to carry a load of 1500 kilonewton with the help of your bearing strength of 9 MPa. Correct? So here again below this particular step, in step number 3rd, we have seen either you may go with providing rectangular type of base plate or you may provide square type of base plate. Correct? So any assumption you may make. So for this particular calculation, we will go with square plate suppose. So adapting square plate, so that will be equal to length of plate equals to breadth of plate equals to under root of your calculated value, area required. So A required, so that will be equal to, so under root of your calculated value, and you are getting answer as 408 mm. So suppose I will round figure that value to 420 mm. Correct? So providing base plate of size 420 by 420 mm. So it is a square plate. We are adapting a square plate. So using this calculated value, now you need to calculate actual bearing pressure on your steel plate. So actual bearing pressure on base plate, we are calculating that using your total load divided by area provided. So as you are round figure the value from 408 to 420, there will be certain change in bearing pressure. So for actual 420 into 420 square plate, you need to calculate this value. So this will be equal to, load given is 1500 into 1000 in Newton divided by your area provided is 420 by 420. So this will be equal to W value, and W value you are getting as 8.50 Newton per meter square, mm square, sorry, Newton per mm square. So this value is less than your characteristic compressive strength M20. So less than 20, sorry, bearing strength less than 9 MPa. So it is satisfying the condition. So we are going to adapt a square plate of 420 by 420 having actual bearing pressure of 8.50 Newton per mm square. Correct? So after these calculations are completed, after this we are going to calculate the thickness. Now for thickness, initially we will draw with this the sketch. Instead of going with here, I will draw that sketch here. So this is the square plate of size 420 by 420 in which your rolled section is provided. Suppose likewise rolled section is there. So likewise are the section details. So I will give the dimensions. So this is size of your base plate 420. Again this particular length as 420, because it is a square plate, we are adapting square plate. Correct? Again for depth of section, so depth of section is 350 given. Correct? Again width of flange is given as BF value, we are adapting equals to 250 value. These two are known value to us, and using the dimensions of base plate and dimensions of your rolled section, you need to calculate the projections. Correct? So I will show here projection. So this is A projection. Again from this side this is A projection. Now vertically beyond this plate this is your B projection, and again at this junction I will show this is your B projection. So likewise along the depth of section A projection I am showing from both the sides, and along the width of flange type I am going to show projection B, because for calculating the thickness longer projection and shorter projection is required. Correct? So here up to this particular step we have decided the size of base plate, that is 420 by 420. Now next is calculating the thickness. So thickness TS is given as under root of 2.5 your pressure into bracket a square minus 0.3 b square into gamma m0 divided by fy, correct, and this value should be greater than thickness of flange, at least that should be equal to thickness of flange. So likewise details are given in formula. So this is as per clause number 7431. This is 7.4.3.1 clause given in your IS 800 to calculate the thickness of base plate. So in this particular calculation, W is actual pressure, already that value we have calculated as 8.50. Now A square and B square, these two values are required and that are defined here. So these are the longer and shorter projections. So initially suppose calculating with A projection, this is A projection, so A projection will be equal to, so that is total size is 420 minus depth section 350 divided by 2 equals to, and B projection will be equal to again 420 minus width of flange, that is 250 divided by 2. So A and B projection we have calculated. So 35 and 85. So 35 mm and 85 mm. Now here you need to remember always, here we have calculated A as 35 and B as 85. So do not put the same values in formula. Always your A should be greater projection, though that value you have defined in the figure as B1. Correct? So values are interchanged. Always the first value should be higher value, and that value is 85 here. Correct? So based on that only you need to calculate. So this will be equal to under root of 2.5 into 8.50. So this value into bracket 85 square minus 0.3 into 35 square bracket complete into 1.1 divided by Fy is 250 yield strength, and this is equal to thickness we are getting as 25.32 mm. So we'll round figure this to 28 mm, which is greater than thickness of flange value is 11.6, is equal to 11.6 mm. Now here you can define provide base plate of size 420 by 28 mm. In the final dimension of base plate, that will be on which your rolled section will be kept, correct. Likewise we are going to provide. So here that design calculations for your size of base plate is completed. Hereafter you need to go for design of connection. So as in the numerical itself, they have asked to calculate or to design the connection using welded type of connection. So for that you need to provide welding all around your I section. So here I will show that welding position. So it will be provided along the entire perimeter of your I section. So likewise will be your welding provided. So likewise welding will be provided. So here you need to initially design the size of welding, correct. So next step, third step and fourth step, size of welding. Now for size of welding we are requiring thickness of thicker part, and we are going to provide thickness welding for thickness of wave and thickness of flange. So greater between these two is 11.6, and according to table, when your thickness of thicker part is between 10 to 20 mm, your size of welding should be 5 mm, correct. So size of welding equals to either S equals to 5 mm or you may provide 8 mm also. In some cases the length of welding provided will be lesser one, correct. So always go for higher side. So instead of adapting 5 mm, you go with 8 mm, correct. So it will be same value. So adapting size of welding as 8 mm, this size we are going to adapt, size of welding is equal to 8 mm. So length of welding possible. So first calculation, length of welding possible equals to, correct. At what particular length we can provide the length here or welding here, so that you have to calculate the length. So here initially that formula is nothing but Simple, just calculate the perimeter. So this is width of flange, again width of flange, 2 times width of flange. So 2 times BF value is the first calculation. Again from inner side also you may provide the welding. So what this particular inner side is, it is width of flange minus your thickness of web. Correct? So that will be 2 into bracket, sorry, it is plus value initially because you have to add all the lengths. So first is from outer side, then plus 2 into bracket. So that will be equal to BF minus thickness of web. Correct? So this is total BF minus thickness of web. That will be total length that can be provided into bracket. Correct? From inner side. Now from this particular web portion and this web portion. So that will be equal to plus 2 times into bracket total H, that is depth, minus thickness of flange. 2 times H minus TF, that is thickness of flange. This is total and 2 times thickness of flange. Yes. Now this value is equal to total. I am directly writing the answer 1663. 1663 mm. This is the total length that can be provided. Sorry, here 2 times thickness of flange minus 2 times thickness of flange. 2 times thickness of flange. So this value is 1663 mm. So at this particular length or perimeter of 1663 mm you can provide the welding. Correct? But what is happening at this particular rounded toes, you cannot provide exact thickness of your welding or exact throat thickness of your welding size is not possible at the toes because the thickness is going to tapered. So in that cases, at every end return, these are the end returns, you have to deduct the value of 2 times size of welding. Correct? So deducting end returns. What are the number of end returns? So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. At 12 times end returns are going to be deducted. Therefore, effective length of weld is equal to, so value is 1663 minus 2 times size of welding, and size of welding adapted is 8 mm. So you are going to get value exactly as 1471. Exact value is 1471 mm. So this is the maximum or effective length of welding that is possible after deducting your end returns at every toe portion or junction at these locations. Correct? So final length of welding provided may be 1471 mm. Correct? Now strength of welding per mm distance. Strength of welding per mm distance. So we are having formula FWD is equal to, that is ultimate design strength of welding is equal to, so it is FU value multiplied by length of welding into 0.707 into size of welding divided by root of 3 into gamma MW. So already we have discussed partial safety factor gamma MW should be 1.5 because this we are doing at directly field. Correct? So putting length of welding as 1 mm. Suppose you are going to provide welding for a length of 1 mm. What will be the strength of section that we are going to calculate here? So this will be equal to FU value 410. Length of welding is 1 mm. Then 0.707 into 8. Size of welding is 8. Divided by root of 3 into gamma W is 1.5. So I am getting value is equal to, strength value is 1313 Newton per mm. So if I am going to provide length for a welding of 1 mm, I am going to get strength 1313 Newton per mm. Therefore, total length of welding required will be total load divided by your strength taken. So that is 1500 into 10 raised to 3 Newton divided by 1313, and this is equal to, so that value is 1142 1142 mm. So according to that particular loading, only 1142 mm length of welding is required, and already you are providing length for a welding of 1471. So it is safe. So it is less than length provided. Correct. So at the last, your connection is completed. At the last, you have to just write here, provide anchor bolts. Provide anchor bolts of M20 at corners. Correct. So at this particular 4 corners, you have to provide anchor bolts. So initially the size of base plate is decided as 420 by thickness is 28. Secondly, we have provided the welding all around the periphery or perimeter of your eye section. So here your numerical is completed. Here important step is you need to just remember the calculation of this particular thickness value, and it is mentioned in your code itself for clause number 7431. So rest simple steps, 3 or 4 steps you have to follow to go for design of your slab base. This particular numerical may be asked for your in semester for 6 marks or 8 marks. So here the video is completed. In next video we will be starting with design of gusseted base. Thank you.